4 astronauts, a spacecraft the size of a small apartment, and a wall of invisible radiation so lethal it could cook your DNA from the inside out. That's what Artemis II flew directly into. And what they found on the other side didn't just surprise scientists. It demolished a model we had trusted for over 50 years. James Van Allen was 33 years old when he strapped a Geiger counter onto one of America's first satellites, Explorer 1, in 1958. The data came back garbled, chaotic. His instruments were reading off the charts, then flatlined completely. Van Allen figured it out. The sensors weren't broken. They were overwhelmed. Surrounding Earth, like 2 invisible donuts of pure electromagnetic fury, were belts of high-energy particles, protons, electrons, trapped by our planet's magnetic field and accelerated to nearly the speed of light. We named them after him, the Van Allen radiation belts. They are, by any reasonable definition, a death zone. Here's what that actually means in physical terms. Imagine standing next to a hospital X-ray machine. One image, maybe a millisecond of exposure, gives you about 0.1 millisieverts of radiation. That's nothing. That's Tuesday. Now imagine that machine is cranked to maximum power, and it never turns off, and you're standing inside it. That's the inner Van Allen belt. Protons so energetic they can punch through several centimeters of aluminum like it isn't there. In the densest regions, unshielded astronauts could receive a lethal dose in minutes. Not science fiction, just physics. So how did Apollo make it through? Simple, clever, ruthlessly efficient. Mission controllers plotted a narrow corridor, a gap between the inner and outer belts near the poles, and flew through it fast. Really fast. The Apollo trajectory was designed to minimize time inside the belts to under 30 minutes each way. Astronauts received roughly the radiation equivalent of a chest CT scan. Manageable, safe, survivable. For 60 years, that model, those belt positions, those flux density maps, that narrow safe corridor, was the gospel truth of human spaceflight beyond low Earth orbit. We were so sure. And then Artemis II launched. The mission was a crude lunar flyby. No landing. Just 4 human beings riding an Orion capsule on a free return trajectory, out past the moon and back. The first humans to travel beyond low Earth orbit since Apollo 17 in 1972. The scientific community was cautiously optimistic. We had the models. We had the shielding calculations. The Van Allen belts would behave exactly as they always had. Crisis averted. We knew what we were doing. That is not what happened. The radiation monitoring suite aboard Orion, a system far more sophisticated than anything Apollo carried, started sending back anomalous data almost immediately after translunar injection. And the numbers were wrong. Not catastrophically wrong. Not everyone is dying wrong. But wrong in a way that made physicists sit up very straight in their chairs. The belt structure had shifted. Not by a little. By a measurable, significant, model-breaking amount. The inner belt's proton flux, the density of those high-energy particles, had changed in shape and intensity compared to what decades of satellite measurements had predicted. And more disturbing, the boundaries between the inner belt, the slot region, and the outer belt were not where the textbooks said they'd be. Let's understand why that matters so deeply. The Van Allen belts are not static objects. They're more like weather, constantly shaped by the sun. Solar wind, coronal mass ejections, fluctuations in Earth's magnetic field, all of these push and pull the belts, compress and expand them, inject new particles or bleed old ones away. We knew this in theory. The Van Allen probes, launched in 2012, spent years mapping these dynamics. They showed us the outer belt could expand dramatically during geomagnetic storms. They even revealed a mysterious third belt in 2013, a radiation ring nobody had ever predicted, sitting between the 2 known belts like an uninvited guest that vanished weeks later. But our models for crude spaceflight had treated the belts as essentially stable enough to plan around, predictable within an acceptable margin. That margin, it turns out, was not acceptable. The sun had been active, historically active. Solar cycle 25, the cycle we're currently in, had exceeded almost every prediction for its intensity. Sunspot counts were at multi-decade highs, solar flares were frequent, and the Van Allen belts had responded accordingly. They'd swollen. The safe corridor that Apollo threaded so elegantly, that 30-minute sprint through the gap, was narrower than the models accounted for. The Orion capsule's shielding performed as designed. No astronaut was in danger. But absorbed dose readings were notably higher than projected, and the spatial data revealed something even more unsettling than the dose rates themselves. The slot region, the relatively empty buffer zone between the inner and outer belts, had partially filled. A transient radiation structure had formed there, born from an injection of high-energy electrons during a geomagnetic storm just weeks before launch. Our models had not incorporated it. Because our models couldn't. Not in real time. Here is what we had wrong. And here is why it might be the most important discovery in human spaceflight planning in a generation. For 60 years, radiation belt models for crewed deep space missions relied on maps that were, at their core, built from 1960s and 70s data. AP8 and AE8, the standard models used for spacecraft shielding design, were conservative by design, built for worst-case planning, not real-time reality. What Artemis II demonstrated is that worst-case planning and accurate planning are not the same thing. The belts during a peak solar cycle look fundamentally different from the belts averaged across multiple cycles. Dynamic particle injection events, things that unfold on timescales of hours, not decades, can create radiation architectures that simply don't exist in our planning documents. We weren't wrong about the physics. The physics is the physics. We were wrong about the environment. We had been planning for a solar system that exists on paper, averaged across time, tidied up into equations. And the real solar system, messy, dynamic, storm-prone, alive, doesn't care about our averages. So what changes now? Everything about how we plan deep space radiation exposure gets rebuilt. The Artemis program has essentially handed researchers the most valuable data set in the history of crewed spaceflight radiation science. Real human beings with real instruments in a real radiation environment during a real solar maximum. Future Artemis missions will carry updated shielding informed by this data. Mission windows will be planned with far greater sensitivity to near real-time solar activity. And the concept of a static safe corridor, the comfortable idea that we could just look at a map and trust it, is gone. The corridor still exists, but now we know it breathes. And here is where the story gets genuinely, quietly profound. There is a temptation, when science gets something wrong, to treat it as a failure, to feel unsettled, to wonder what else might be incorrect. But look at what actually happened here. We sent humans deeper into space than any human had gone in half a century. We measured. We discovered the discrepancy. We will now build better models, plan safer missions, and understand our own solar system more accurately than we did before. That is not failure. That is the scientific process working exactly as it should. Beautifully, humbly, correctly. Van Allen himself, sitting in a control room in 1958, watching his instruments flatline and realizing the universe had just handed him a mystery nobody knew existed, would have understood this moment perfectly. The belts he discovered are still surprising us, still teaching us, still reminding us that the space between Earth and the Moon, the thin slice of cosmos that humans have only ever barely touched, is far more complex, far more dynamic, and far more alive than our most confident equations ever suggested. We weren't wrong because we were careless. We were wrong because the universe is extraordinary. And we are only just beginning to listen.